In this lecture, we're going to discuss Taylor's theorem. Now, this is really a very marvelous theorem, and although it's something like 250 years old or more, nevertheless, it's very, very fundamental, very powerful. And what it says is that if you want to know what a function is anywhere, all you need to know is the derivatives at one single point. And so for a whole class of functions, if you can find the derivatives at a single point, then you can know the function everywhere. That's really remarkable, but let's approach this step by step. Let's quickly establish some notation. This is going to be called n factorial. That means if n is 1, 1 factorial will be called 1, 2 factorial is 2 times 1, 3 factorial is 3 times 2 times 1, 4 factorial is 24, 5 factorial is 120. You see how rapidly it is growing. By the time we are up till 8 factorial, we're at 40,320. And so n factorial is a very, very rapidly growing function of n. Now let's come to what we are really after. Here is a function f of x, which means that as x changes, f changes. Now let's say that we want to look at it close to x equal to 0. In that case, if we were to say that f of x is a constant value, that would not be very accurate, in fact quite bad. If we were to say that instead it is a straight line which goes up like this, then it's somewhat better, but it's only good very close to x equal to 0. It would be so much better if we could give it some curvature like this, and in that case we would have a better approximation. So let's say that we were to approximate f of x by a constant plus another constant times x plus more constants with appropriate values of the power of x and so forth. Will this work? And how well will this work? Let's look at some examples. Let's take an actual function, 2 plus sine x. You can see that when x is equal to 0, its value is 2. And so let's approximate this with a constant function whose value is 2. As you can see, it's not doing very well. And so let's try a straight line fit. Now this does better because you can see that near x equals 0 or y equals 2, this is doing a reasonably good job. However, we can do better. And now we have 2 plus x minus x cubed over 6. So we've gone to 3 powers of x, and you can see it's better. It becomes still better when we go to 5 powers of x. Now for the time being, don't worry how those coefficients came about, the 1/6 and the 1 over 120. We will come to that in just a little while. But I'm going to add on 1 more power of x, or rather 2 more powers of x. And you can see that adding more and more terms, more and more powers of x, is making the fit better and better. Let's take another example. Here is the function e to the x over cosine of x. And this is a function that at x equals to 0 is 1. Obviously e to the 0 is 1 and cosine of 0 is 1. And now let's approximate this with a constant function whose value is 1. As you can see, it doesn't do very well. So let's use 1 power of x. As you can see, it's doing a little bit better, at least close to x equal to 0, it's pretty good, but then it deviates. Here are 2 powers of x. Now you can see that the agreement is quite a bit better than it was with a straight line, but There's still quite a lot of deviation. Now go to 3 powers of x. You can see that it's gotten a lot better. Here are 4 powers of x, and you can see that we've started to do very well indeed, except that there's a deviation as we go towards the left. So basically what we've done is we've expanded f of x as some constant plus another constant times x plus a second constant times x squared and a third constant times x cubed and so forth, and we can go until we get tired and write down the final one, an x to the n. Now these are numbers a0, a1, a2, etc. The question is, how do you find them? That's easily done. Let's put x equal to 0, in which case f of 0 will be a0, and we found the value of a0. Let's now take the derivative of f, that is f prime, in which case a0 will be eliminated, and from here we will get a1, but from here we'll get 2a2x, from here we'll get 3a3x squared, but we can eliminate all of these by just putting x equal to 0, and so f prime at 0 will be a1, and so we found a1. Now let's take 2 derivatives and put x equal to 0. So the first 2 terms will be eliminated, but the second one will give us 2a2, and the remaining terms, once we put x equal to 0, will be 0. Now we found a2, let's go on to a3, which means taking 3 derivatives and putting x equal to 0, in which case this is the term that will matter, a3 x3 cubed. And from here we will get 3 into 2 into a3. In this manner, we found that a0 is f0, etc. And we found that in general, an can be got by taking the derivative of f n times, putting x equal to 0, and dividing by n factorial. So this brings us finally to Taylor's polynomials and Taylor's theorem. Here's what I mean by Taylor's polynomials. So for example, p0 of x is just the constant value f of 0. p1 of x, that is to say the first Taylor polynomial, is f of 0 plus f prime of 0 times x. In other words, this is the equation of the straight line with which we are trying to approximate the function f of x. And etc. We could keep going to p2, p3, and so forth. Now here comes Taylor's theorem. It says that suppose f of x is a function which has got at least n plus 1 derivatives. In other words, you can keep differentiating this at least n plus 1 times. If you can't differentiate it, then Taylor's theorem is not useful at all. So Taylor's theorem says that the function is exactly equal to the Taylor's polynomial of order n plus a remainder term. This r over here stands for remainder. If this remainder was 0 or very, very small, then you'd be very, very happy. But in general, this remainder will not be 0. How big is it? Here is the real crux of Taylor's theorem. It says that the remainder term is this thing. That is to say, the n plus 1th derivative of f evaluated at some point c, which lies between 0 and x. So in other words, if you're trying to approximate this function, which is like this, and you know all the derivatives of f, then if this is the point x, then this point c lies somewhere between here and here. It could be large, it could be small. If it's large, then the remainder term is going to be large, in which case this is not going to be very good. But on the other hand, if the remainder is small, then you're in good luck. And you're going to get a very accurate representation of f. Let's now work out a number of examples beginning with f of x equals sine x. Of course, if we take the derivative, it's very simple. It's cosine of x. The second derivative will be minus sine x. And now it's getting too many primes over there. So f3 of x will be minus cosine x. f4, that is to say the fourth derivative, will be plus sine x again. The fifth derivative being cosine x, and so forth. We can, of course, keep going over here. Now you notice that f at 0 is 0, f prime at 0 is 1, and f double prime at 0 is 0, and so forth. So the function f of x is x minus x cubed over 3 factorial plus x to the 5 over 5 factorial. And you can guess that the next term is going to be minus x to the 7 over 7 factorial, and so forth. And so let's call this P7. That is to say the Taylor polynomial of order 7. And what's left over is the remainder. Now this remainder is going to get smaller and smaller for any fixed value of x as we increase the number of terms that we include in the Taylor polynomial. Let's now take another example. Here's f of x equals the exponential of x, and you can see that the derivative and the second derivative and the third derivative, these are all equal to e to the x. And so the values at x equal to 0 are all 1. So f prime, well, f of 0 is 1 and f prime of 0 is 1, and they're all 1. That means that we can write down the Taylor's polynomial of order n very easily. So Taylor's theorem tells us for the exponential we have 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed. And if we want to go up till n terms, that's 1 over n factorial x to the power n. Now that's the Taylor's polynomial. This over here is the Taylor's polynomial of order n. And this is not yet an equality. There is still a remainder. This remainder is going to get smaller and smaller for a fixed x as we go to larger and larger n. Let's work out Taylor's theorem for the logarithm. Taking the derivatives is again very easy. F prime of x is 1 over 1 plus x. F double prime changes sign, and it's minus 1 over 1 plus x squared. If I take the third derivative, then the sign changes again, and I get 2 over 1 plus x cubed. The fourth derivative changes sign again, and we get minus 3 into 2 over 1 plus x to the 4. And now the pattern is very clear. So we have the function at the origin at x equal to 0 being 1. The first derivative is 1. The second derivative is minus 1. The third derivative has changed sign. It is plus 2. And the fourth derivative is minus 3 factorial. And I could write this as 2 factorial. It's the same thing. So let's write out Taylor's theorem. F of x is then just equal to x minus x squared over 2 plus x cubed over 3. And of course, we could go beyond it. The pattern is very clear. The next term will be minus x to the 4 over 4. But let's stop here and write this over here in the form of Rn plus 1, that is to say R4. So this is the remainder that includes terms of order x to the 4, 5, 6, etc. So the hope is that this over here, which is the third order Taylor polynomial, is going to be a good enough approximation to the logarithm of 1 plus x. Now, sometimes it is possible to write down a Taylor series without doing differentiations. Here's an example of that. So now I have f of x is 1 over 1 minus x, and I claim that this is equal to 1 plus x squared plus x cubed plus x to the 4, and this keeps going on. I can easily check this, because if I multiply 1 minus x with f of x, then I should get 1. Well, let's see if we do. I have 1 minus x, and what is up above is 1 plus x squared plus x cubed plus x to the 4, etc. And we can keep going over here. Now, opening this out, if I just multiply 1 with all of this, I get 1 plus x squared plus x cubed plus x to the 4, etc. And now I multiply with minus x, so I get minus x squared minus x cubed minus x to the 4th, and so forth. So all of these terms are going to cancel, this with this with this, and so forth. So we're going to get 1 at the end. Now, we could have easily done this with just taking derivatives as well, but that would have been longer. Taylor's theorem is useful if the remainder term is small. Just to remind you about Taylor's theorem, here it is again. You can open up or expand a function f as a Taylor polynomial, and then there's a remainder whose explicit form is given over here. What we need to do now is learn how to use this formula. So let's do that with a couple of examples. First of all, we want to know how much error you get or you make by using only 1 power of x in the expansion of e to the x. So if I have e to the x, I expand this out, I get 1 plus x, and then there's a remainder which we'll call R2 from above. R2, if we look up over here, is the second derivative of the function evaluated at x equal to c divided by 2 factorial, and the value of x that we're considering is 0.2, so that gets squared. If we differentiate the exponential twice, well, you get the exponential itself, and so we have e to the power c over 2 into 0.04. And now the question is, what is c? Looking over here, we are told by Taylor that c has to be a number that lies between 0 and 0.2. Now, that is going to involve the use of a calculator, and I don't want to do that. Therefore, what I'm going to do is simply estimate what e to the c is. I certainly know that it's going to be bigger than 1 and less than 2, and so the magnitude of R2, which I'm concerned with, is going to be less than, so it's going to be less than 0.04. In other words, my accuracy is going to be about 4%, or maybe better than that. Well, let's look at the exact value of e to the power 0.2, and for that we need a calculator, and the calculator tells me that it is 1.2214. 1.2214. And so the exact error that we made was from here 0.0214. 0.0214. And that's fine. I estimated that the error is going to be less than 4%, whereas actually the error is 2%. And for a rough calculation, that's perfectly fine. Well, let's take a second example. Here, sine of x has been expanded out to 1 power. And so the remainder is R2 again. And this R2 is the second derivative of sine of x. So we differentiate it twice and evaluate it at x equal to c over 2 times 0.1 squared. That's just the formula up there. If you differentiate sine once, you get cosine x. If you differentiate cosine, you get minus sine x. So that's minus sine c over 2 into 0.01. Now, I don't really want to do an accurate estimate. All I need to know is that sine of c is less in value than 1. And so the magnitude of R2 is going to be less than 0.005. On the other hand, if I look at sine of x exactly, so if I look up the tables for sine of 0.1, sine of 0.1 exactly, that is 0.0998, 0.0998, and the error is 0.0001. So you can see that I've done a good enough rough job. You see that the error is something like 0.5%, whereas it is even less than that. What we've done so far is expand around the point x equal to 0. So, for example, if this is the curve, then we simply say that we shall match the slope over here and the curvature over here and so forth. But what happens if, let's say, we have a point A and we want to expand about this point here? So, if, let's say, h is a small distance away, then it's perfectly clear that f of a plus h in that case will be f of a if h is 0. And if h is small, then this should be good enough. The derivative f prime evaluated at the point x equals a. If h is not small enough, it's a bit larger, then you may need to go to the next term, h squared over 2 factorial f double prime of a. And then there's the third order and the fourth order and so forth. Or you could write it differently. You could say, okay, if x is a plus h, then in that case, f of x is being expanded as follows. F at the point, here h is 0, so f at the point a plus h. Now instead of h, I'm going to write x minus a, and the derivative is to be evaluated at a and so forth, and so 1 over 2 factorial x minus a squared f double prime and so forth. So this is our Taylor's polynomial. To understand better, let's apply what we've just discussed to this function, which is a polynomial, and make instead a Taylor polynomial centered around a equal to 1. So in other words, we want to expand this function about a equal to 1. We've already discussed that. So if we take f of a plus h, that's the value of the function at 1, and then we need the first and the second and the third derivatives and so forth. So f at the point a equal to 1 or x equals 1 is 3 plus 1 minus 2 plus 1, which is 3. Take the first derivative, that's 1 minus 4x plus 3x squared. And when I put x equal to 1 or a equal to 1, that's 0. Take the second derivative, that's minus 4 plus 6x. And when x is 1, that is equal to 2. Take the third derivative, and that is 6. Take the fourth derivative and the fifth derivative, and so forth. All of these will be 0. So here is the Taylor's polynomial. F of a plus h is 3 plus h times 0, of course. And then there's half of h squared, and there's 2 here, and then 1/6 h cubed times 6, and that's it. And so this is 3 plus h squared plus h cubed. Now we could write this in the following form. F of x is 3 plus x minus a squared plus x minus a cubed. Now you could have written this down directly, and here of course a is 1, so we could write this as x minus 1 squared plus x minus 1 cubed. And you could have written this directly looking at this function. The two are exactly the same. And so for a polynomial, a Taylor series truncates. It stops after a point, and in this case it stops at the third order term. There is no remainder. The Taylor series is exact for a polynomial. Here is a fact that's useful in many applications of mathematics, and in particular Taylor's theorem. It says that for any fixed number x, and so let's take for definiteness, let's say x bigger than 1. So it could be 20, it could be 19.3 or whatever. Then x to the power n divided by n factorial is claimed to approach 0 as n becomes bigger and bigger. Now this is not altogether clear because x to the n becomes larger and larger as n becomes larger, but so does n factorial become larger. The question is, which of these wins? So here's a very simple way of proving this. Suppose that x is less than some number, let's call it capital N. So if x is 19.3, you would take n to be 20. If x is 100.2, you would take n to be 101, and so forth. So let's write x to the power n divided by n factorial, small n factorial, to be the following. It's x over 1 times x over 2, and we'll keep going until we reach x over n, capital N. Now notice all the numbers over here are bigger than 1, but then in the next bunch of terms we're going to write all those numbers which are less than 1. So x over n plus 1 is certainly less than 1. And then we're going to get x over n plus 2 and so forth, finally ending at x over n. Now here all the numbers are multiplied together and they give you some fixed number, whatever that is. It could be very large, but now look over here. Here we are multiplying a bunch of numbers, each of which is less than 1, and because n can become larger and larger, we can keep multiplying by smaller and smaller numbers. And so although this is finite, this over here will go to 0. And hence, the limit of x to the n over n factorial will be 0 as n becomes larger and larger. Let's now use this fact for the Taylor expansions that we've derived earlier. So here is the expansion for e to the x. This over here is a Taylor polynomial, and there's the remainder part. Here it is for sine and cosine. Now, in each case, the remainder Rn plus 1 is evaluated at some point x, and it's a fixed value for the derivative, just call it fn plus 1, times x to the n plus 1 divided by n plus 1 factorial. Now, as n goes to infinity, we've just discussed that this factor over here goes to 0, and hence the remainder also goes to 0 for any value of x. And that's saying that as long as we fix x and increase n, we're going to get accuracy, as accurate an answer as we like. All we have to do is include more terms. In many situations, the Taylor expansion is extremely useful, but there are places and cases where it fails, and fails spectacularly. Here is the function f of x equals e to the minus 1 over x squared. And first of all, let's ask, what is the value of this function at x equal to 0? Well, it's e to the minus infinity, and that's 0. Let's ask what the first derivative is, f prime of x. Well, if we differentiate the argument of the exponential, we get 2 over x cubed, and then the exponential again, e to the minus 1 over x squared. Now, as you make x smaller and smaller, certainly this factor over here, 2 over x cubed, becomes infinite, but this becomes 0 even faster, and if you take the limit of the 2, this goes to 0. So f prime of 0 is 0. If you now take the second derivative of f, it turns out that at x equal to 0, and I won't do this calculation here, you can do it, this is again 0, and in fact every derivative of this, so fn, the nth derivative evaluated at x equal to 0 is 0. So what we have for Taylor's theorem is that f of x is equal to 0 plus the remainder. And so the remainder and the function are the same. This Taylor's polynomial over here is of absolutely no use. Such a function is called non-analytic. It does not have a Taylor polynomial expansion. You can understand this result by looking at the graph of e to the minus 1 over x squared. If you look at the origin or close to it, you see that every derivative of this function is 0. It is exceedingly flat, and in spite of all derivatives up till infinity being 0, nevertheless this function is clearly non-zero. In the lecture so far, we've concentrated more on the behavior of a function at a single point. So the first, second, third derivatives and so forth. Now that's the local behavior of a function. What we're going to be looking at in the next several lectures is integral calculus, and that deals with the function and its properties over a larger domain. That'll be the next part of this course.